Hey guys, going on to addition reactions of alkenes. So in this chapter, a little bit of an overview, we're going to learn how to go from a double bond and place on a bunch of different compounds in place of that double bond. And we're going to learn different, whether it's the least substituted carbon or the most substituted carbon, or we're adding two different, I guess, substituents, you could call it, two different things to your double bond. We're going to learn all those different ways in this chapter. This is your first main chapter where you're going to learn a lot of reagents if you haven't already, with all those, substitution and elimination reactions. You're going to be actually learning how to do multi-step synthesis. So you go from a double bond, maybe you put on a bromine, maybe with that bromine you do SN2 synthesis, and you could put on an NaOH and you put on an alcohol group. So you're going to be learning all those ways. Here are the major names of the game here. So you have hydrohalogenation, and you can see for all of these I have made a different color for all the keywords in the names for these reactions. So if you can't tell, hydrohalogenation deals with putting a halogen onto a double bond, and we're going to go through each one of these. So let's just get started. So hydrohalogenation is exactly what you think it means. It's putting a halogen on your double bond. So I have what's going on here. We have a bromine or chlorine attacks the double bond on the more substituted carbon. So whenever you see a double bond, you really want to search out, well, is this primary, secondary, tertiary on both sides of the double bond? And that is where your halogen is going to be, on the more substituted carbon. And you can see that that double bond, it doesn't disappear, but it goes away, and in place of that gets placed that halogen. Okay, so that's the first reaction. You can see right here, I have a double bond, and your halogen will go right there, and that's what happens on this side. And I have HCl right there. It should be HBr because we're putting a bromine on, but that's that first reaction. So let's do this example. We have, let's see, on both sides, this has a primary a carbon, and this is a tertiary. I'm sorry, that's a secondary. That might be a tertiary. Let me look. 1, 2, I believe that's a tertiary carbon. Whether it's a secondary or tertiary, that's still better than that primary, and that's where that Br is going to go. It's going to attack right there. Obviously, in a mechanistic step, and you guys will probably have to learn the mechanism to all these, or at least most of them, that double bond gets taken away. You put a carbocation there, and then you put that Br. So what I mean by that is that your first step is taking out that double bond. You get left with that carbocation. That bromine then attacks that double bond, or attacks that positive charge, and you get left with this product. Remember, the more substituted carbon is where that bromine will attack. So that's hydrohalogenation. If you add ROOR to the bottom of this reagent, it will then attack at the least substituted position. So for this example, let me rewrite it. Let's say we had the same example, but instead of HBr, we add this ROOR. It will then attack at the least substituted carbon. So it'll now look like that, because this was a primary carbon, and it's going to attack there, the Br is. So adding that ROOR, and it's typically shown below that arrow, and you'll see HBr, you can see HCl, whatever it is, it then attacks at the least substituted position. So that's really important for synthesis. Acid-catalyzed hydration. There's a couple keywords here. Acid, so we're dealing with some sort of acid, and it's hydration. So you're adding an OH, you're adding alcohol. So there's a couple keywords there, and I wrote here that an alcohol group gets added onto the more substituted carbon over the double bond. You can also use dilute H2SO4 instead of H3O+. You'll probably see a lot of H3O+ instead of that dilute H2SO4. but they both do the same thing. So in my example right here, we have a secondary carbon and we have a primary carbon, and that alcohol gets placed on the secondary carbon. Same thing right here, we have a tertiary and we have a secondary, so that alcohol will be placed right there. And you can see for most of these reactions, I guess pretty much all of them, that the double bond gets taken away in place of something. It just matters where and on what substituted carbon you're placing it on. And then in a little bit, we're gonna focus on the stereochemistry of it all too. So some sort of examples I have right here. Let's look at, we're looking at this double bond and we want to figure out which is the more substituted carbon. We have a 2 and a 3 and we pick that 3. So it's pretty much as simple as that. The big deal with this chapter is just memorizing all these reagents. So you put that alcohol group right there. And for most of this chapter, it's just memorizing these reagents is the big worry for most students. Obviously, we have a secondary and a tertiary. We want to pick that tertiary. So that alcohol group will be right here. And we have dilute H2SO4. You guys are also going to see this as well. It means the same thing as well. So for this one, we're finding the most substituted carbon, which in this case, this is third, this is second. So we're picking the third. It's as simple as that. One thing that I didn't write here is that this is subject to rearrangement. So if you see, I didn't really have any questions like that, but if you see a carbocation that forms right here, that H3O plus can rearrange, and you can rearrange your carbocation to go on a more substituted carbon. So that is possible with this, and you'll see in a minute that we do have a reagent that is not possible for rearrangement. So one thing that we did before, if you guys remember from the substitution and elimination chapter, is concentrated H2SO4 instead of dilute H2SO4. So concentrated SO4, we already start with an alcohol, but that will form into a alkyne. So that's a big deal. So same thing for this one. It goes on the more substituted carbon. So that's how you can go. That's the difference between dilute H2SO4 and concentrated H2SO4. So this is the one that cannot rearrange. This is oxymercuration, demercuration. So you have a very complicated reagent right here, and it has a two-step workup, you could say. It has HgOAc2, comma H2O, and then NaBH4. So it has two parts to this, and I know it's a lot to remember, but you're just going to have to do it. And this one, an alcohol group, again gets added to the more substituted carbon, but this one, it cannot rearrange. So how I was saying that you can move that carbocation over to a more a better position over, the hydrocarbon chain, you cannot do that for oxymercuration, demercuration. That's the difference. So for this example right here, how would you do this? You would look at the more substituted carbon. So this is secondary and this is primary. So you want to add that alcohol group right here. And that will be the end of this. And then I put this example as well for this H3O plus, because the difference is when you get this carbocation, you can switch it. So then that carbocation does a hydride shift. It's called a hydride shift. And this is the difference between the two. It does a hydride shift. So then your OH group will end up on a more substituted carbon. So obviously there's mechanistic steps to all of this that I'm not going over, but it's important to know the difference between oxymercuration, demercuration, and acid-catalyzed hydration. Going on to hydroboration-oxidation, some couple things that I noted here is that there's a hydro and then an ox. That's a dead indicator that you're adding oxygen and hydrogen. So you're adding that OH group again. But what's the difference here? What's the difference between what we looked at before, where this gets added here, and the difference where it gets added here now? You can see that it now gets added on the least substituted carbon over the double bond. So this was secondary and this is primary. You're adding it on the least substituted carbon. So that's a pretty straightforward one. And again, it takes a little bit of practice to remember all these reagents: BH3, THF, H2O2, NaOH. It's a lot of steps. There's 2 steps in this reaction. So yeah. So for this example, let's look at our carbons over the double bond. This has a secondary and this has primary. We want to add to the least substituted carbon. So our OH group will end up on that primary carbon over that double bond. Let's do one more example on this. Let's say we had, let's put the double bond right there. Where would you, and again, let me, BH3, TH4, H2O2, NaOH. Where would you put that OH group? Well, we have a tertiary and we have a primary. So that would want to go over here. All right, so all of these are important to this overall chapter. So it's important to remember all of these. So next one, we have catalytic hydrogenation. So again, that hydro is a dead indicator. We're dealing with a metal now. So PT on the end of that arrow, we have H2PT. So this will take an alkene and reduce it into an alkane. So this is really important. And when we get into the alkyne chapter where we're dealing with triple bonds, we'll see this reagent again. But this can reduce alkenes into alkanes. So this is a very important reagent as well. So you can see we can also use PD instead of PT. And you'll see probably a slew of different reagents on that bottom arrow because there's different ones you could use. But what will this do to this? It will just take out that double bond. So you'll be left with nothing else changes but that. So that's your answer. All right. Halogenation is just like the term suggests, but we are adding 2 halogens for this one. This one's super easy because it says it in the reagent already. Cl2 suggests that you're adding 2 chlorines. You could also write Br2, stuff like that. So I wrote Cl2 and Br2 adds a ClBr in each position over the double bond, one with a wedge and one with a dash. So this is called anti-addition. And why, you might ask, I didn't add a dash for this one is because you only write wedges and dashes when you're dealing with chiral centers. So it wasn't really appropriate to show a wedge for that one, but it is important to know that this would be anti-addition if that second chlorine was on a chiral center. Okay, so I have an example down here. We have Br2. So we have to look at our double bond and we add a Br to each of that. So we have one B that's on a wedge and one Br that's on a dash. And that's it for that reaction. All right, our getting into, we added 2 halogens over the double bond. Now we're adding 2 alcohol groups over the double bond. We have anti-dihydroxylation. I don't know why that was so hard for me to say, but for this one, we have anti. So that anti suggests that we're dealing with anti-addition. So let me write that over here. This is anti-addition. So just how we had 1 wedge and 1 dash over the double bond for our halogenation, we're doing the same thing. Obviously, again, for this example, I didn't write the dash here, but that's, if you learn better that way, that's perfect. So I wrote, these reagents add two alcohol groups over the double bond, one as a wedge, one as a dash, why it's called what it's called. And remember that R in RCO3H can represent any compound. So for my example right here, we put a methyl group in there. So don't get tripped up on a quiz or an exam when you see CO3H and there's something instead of R there. It means the same thing. You're just dealing with an actual compound instead of R. So what would we do for this question? Let me write out the same compound without that double bond. We would add those alcohols in anti-addition. So one could be, let's put this one as wedge and this one as dash. And there's two OHs over that double bond. And then enantiomer, if you remember what enantiomer is, you would have a plus enantiomer because you could also write this. So you could also write this as a wedge and the other one as a dash. That would work as well. And this one would be the same thing. You could have a dash here. All right. So instead of anti-addition, let's do syn-addition. Syn would be the same. So they would be the same stereochemistry. So if you have two dashes, if you have two wedges, they would be the same. For this one, we're adding two of the same alcohol groups. So we use OS, O4, H2O over your arrow, and that gets you two alcohol groups over the double bond, which could be either wedges or dashes. And I wrote in here that syn means same, so you could add what I added up there, or you could add KMNO4 NaOH. So don't be afraid if you see that over the double bond as well. That means the same thing as the reagent I used up there. It will result in those two alcohol groups being placed over that double bond. And you can also use, and you guys are really going to get into this when you talk about the alcohol chapter. I know we're adding alcohols, but when you really get into the alcohol chapter, you're going to be dealing with this MCPBA that's used for epoxides. But if you add H3O plus, you can make what we made with our OSO4 H2O as well. So for this example, all we have to do is take out that double bond and either add two wedges or two dashes. I'll add two wedges for this one. And you could do plus enantiomer to show that there's another compound that you can make with this. All right, oxidative cleavage is just that cleavage means you're, spreading apart something. So you're taking away that double bond, you're splitting into it. So you can imagine when I went through this course, I would imagine splitting, and I would write this on my paper. I would put a line right through this double bond, and either side of that is what you get as your product. So if you have one reactant on one side, you should end up with two products with this oxidative cleavage. And I put an example right here. So in place of each side of the split is an oxygen double bonded. So that's very important. So for this one, think of it being split and just write what it would be on the other side. Remember, your carbons should stay the same as well. So we have 1, 2, 3 carbons on this side. We have 1, 2, 3 carbons. We have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. So your carbons should stay the same. You're just adding that double bonded oxygen to each side of that split double bond. All right, so other reactions that I didn't go over, but I went over in this previous chapter was this TSCl pyridine. That's how you get a bad leaving group into a good leaving group. So you saw that in substitution and elimination reactions a lot. Another one that is in this chapter, but not really covered too much, is that Br2H2O. And this one's pretty easy because Br2, that should signal you're adding a bromine, and this H2O, you're adding an OH, an alcohol group. You're adding both of those to this. The only difference is that this alcohol group is on the more substituted carbon. So that's an important one as well. This MCPBA you're going to use in the alcohol chapter a lot. You really don't know what an epoxide is yet. But if you don't use a secondary step in H3O plus, you end up with that epoxide. But say we did add MCPBA with H3O plus, that would give you your two oxygens as well. Okay. So these are all the reactions that I just went over. So if you want to, screenshot this or whatever helps, these are all the reactions you're going to see in this chapter. Some other ones that you guys, will see probably in the radicals chapter is this NBSHV, where you can just add a bromine group to what seems like nothing, but it's using an alkane and adding that bromine group to the more substituted carbon. So that's one that I didn't really go over either. But these are all the different reactions for this chapter. So in next video, I'm going to go over a slew of practice problems and multi-step synthesis. So if you're worried that I didn't go through any practice problems, watch my next video. I'll see you guys later.